introduction so we can
Oh,
get
dear.
started. Not that formal.
I just want to say thank you for coming out. Welcome to the library. We are excited to have Dr. Nick Castle here with us again. And I wanted to note, please save the date for his following two lectures, Asteroid Mining for Dummies on Tuesday, April 28th, and then Science and the Art of Storytelling on May 12th. Just briefly, Dr. Castle is a research scientist at the Planetary Science Institute. He's a graduate of Lehigh, the University of Washington, and the University of Alberta. And he has 25 years of experience studying geology, planetary science, and the how-tos of space exploration. He's worked with the Jet Propulsion Lab for the past 7 years as a mission operator with the Curiosity rover, and he's an aspiring mission planner developing proposals to study volcanoes on the Earth, the Moon, and Mars. So welcome again, Dr. Castle. If you're joining us on Zoom, feel free to put any questions in the chat, and I will raise my hand and read them out loud. Thank you.
Thanks very much. I do enjoy an informal lecture style, so if you have burning questions along the way, if I missed something or said something silly, or you just want to know more, please ask. If I can, I'll stop and answer it. If I can't, I will ask you to wait patiently till the end. All right, so thank you for the introduction. As Courtney mentioned, my name is Nicholas Castle. Nick, Nicholas, hey you, it all works. Here we're going to talk about a brief tour of the solar system. Now, I should mention my bias before I begin any talk. I'm what's called an igneous petrologist. That is, I study rocks that come out of volcanoes. That means my interests in the solar system are things that are solid. Not terribly interested in the sun, not terribly interested in gas giants, not terribly interested in things that aren't rocks. So you're going to hear a lot more about rocks than you are about everything else in the solar system. But if you want to hear about the other stuff, let me know sometime and maybe they'll invite me back for another lecture. So what are we going to talk about today? Well, before we talk about all the objects in the solar system, it's really helpful to talk about, okay, basically what's there, how did it get there, and where is it? So these are the questions we're going to ask and answer before we really get into a tour of each of the different objects that I'm going to talk about today. Don't worry, we'll get into pretty pictures of planets, but first we're going to do some background science and introduction. So, what exactly is in the solar system? If you went through grade school like I did, then at some point you probably saw a picture that looked something like this. Not exactly this one, this is my cartoon. I drew this one. But these are the objects in the solar system, by and large. If you're curious about their names, we've got the sun is the curvy object on the left. It is huge compared to the rest of the solar system. These are not size accurate in terms of where they are, but they are size accurate in terms of their relative proportions to each other. The sun is massive. Mercury, Venus, the Earth, and Mars, the 4 dots on the left, tiny by comparison to the rest of it. Then we've got Jupiter, which is, it's something like 1% of the solar system's mass, the sun being 99%, give or take. Saturn is the rounding error on what I just told you, and Uranus and Neptune are another sig fig smaller. Jupiter, Saturn, Uranus, and Neptune, much, much larger than Mercury, Venus, Earth, and Mars. So if we start talking about what's in the solar system, it's helpful to start making categories of things. What belongs together? What stands out as different? So if we make categories out of these, we're talking about the terrestrial planets, or terrestrial worlds. I like to include moons. And the gas giants. We also now talk about ice giants, and the reason why, if you went through grad school with me, you would have learned we had 4 gas giants. Now we talk about 2 gas giants, 2 ice giants. And it's just because there's a lot more solid material on the interior of Uranus and Neptune than there is on the interior of Jupiter and Saturn relative to its full size. We want to denote that difference, so we call them ice giants. Gas giants is fine too, but if you want to be technical. Now, what else is missing from this picture? Who knows another object that's floating around the solar system? Perhaps big rocks. Moons. We'll get there. Asteroids. So we've got an asteroid belt that's sitting between Mars and Jupiter, and it's made up of chunks of rock that are floating around in space. Who here's ever seen a comet? Comet, if you went through grade school, you were probably told is a ball of ice that has a long tail coming off of it. Oftentimes we like to picture that tail as being, pointing backwards in the orbit. It's not. It's pointing away from the sun because it's the solar wind that's blowing that tail off of it. And comets are volatile rich, meaning they've got lots of ice and other gases on them, that when they heat up close to the sun, makes a cloud, and then the solar wind blows them back away from the sun. And you get this long tail as it gets into the inner solar system. This is a pretty basic picture of the solar system. That's what's there. So we can all go home now, right? Who wants to know a little bit more detail about this? If you want to get into more detail about what's in the solar system, it's really helpful to know, well, how did this stuff come about? So let's talk about that. How did the solar system form? What did we have before there was a solar system? Does anybody know?
Nothing.
Nothing. You know, statistically, you're right. But there's just a tiny little bit of something. What we had is what's called a nebula. Nebula are large clouds of gases and dust that are floating around in space. And my silly little picture of it is because I was cribbing an actual picture of a nebula. This one is Messier 20, also known as the Trifid Nebula. And it's what's called a star-forming nebula. These clouds of gas and dust, every now and then something comes by that bothers the cloud, makes it gravitationally start to collapse. This could be a supernova went off, which literally puts a shockwave through the cloud, or it could be something really big and dense like a black hole went by, or a very large star. Something happened that perturbed it from its nice big diffuse cloud, starting to form stars. So that's the next thing that happens, is you start to make little stars in it. Now what does that actually look like when you do that? Well, to do that we've got to zoom in on one of those stars. And what you'll see is a little pinprick of a star surrounded by a black area around it, and then the nebula continues along outside of that. And what's going on is the nebular gas and dust is being pulled into that gravitational center. The snowball that's building is going to become a star. And you can actually see this in the zoom in of the Trifid Nebula. Right around here, you can see a little star, and then there's this big black cone that's pointed behind it. My drawing is just a cartoon and it's stationary. If it were moving, it would sweep out a cone behind it. And that's exactly what's happening. The star is moving relative to the nebula, and it's eating the nebula as it passes through, building itself up to make a star. Well, that's great. That gets us the sun. But we kind of want to know about how did the planets get here, right? I mentioned I like rocks, not stars. So how did we get rocks around this thing? To talk about that, we've got to look even closer at that forming star. Here's our nice little protostar. It's a ball of gas and dust that's piling up together and making a bigger and bigger snowball. And it's doing it by pulling in mass from all around it. Now the thing is all those little bits of matter, all the little bits of stuff around it, aren't coming straight into the gravitational center. They're moving relative to each other, so they miss the star just a little bit, which means they've got some angular momentum in the system. What that means is the whole thing starts to spin as it collapses. And when it spins, what happens to a ball? Who here's ever thrown a pizza? You start off with a ball of dough, you spin it up and it elongates out and you make a disc. That's not exactly what's happening here. What's happening is most of the matter is still falling into the star, but as it's spinning, some of that matter has enough velocity that it doesn't hit the star, it stays in orbit and enters a stable orbit. And eventually that piles up and makes a cloud around your protostar. That's your planetary disk. Sound neat? Well, one of the things you always want to ask is, pictures or I don't believe you. Well, astronomers, lovely people that are not me, take pictures of things, and once in a while they find stuff like, here is the HL Tauri system, which is a planetary nebula. You've got a star that's forming right in the center, and the whole rest of this is what we call that planetary disk. That's that spun up material that was falling in and had enough velocity to stay in orbit instead of collapsing into the center. Pretty cool, right? Well, what's one other detail I haven't explained yet that's up here? What's something that stands out to you? Does it remind you of any feature you've maybe seen pictures of in astronomy of the solar system?
Rings?
Rings. It's not just a disk, it's got dark spots and light spots through it. Those are gaps. And what's happening in each of those gaps is you've got a planet that's forming in each of those orbits. How does that work? Well, let's zoom in even further. If I zoom into one of those gaps, in just the right spot, you would see a planet that was sitting in it, or a protoplanet. What's going on is you've got a little ball of mass that's sitting there. It's got enough gravity that it's starting to pull in material from the rings to either side of it. What happens is you've got stuff that's orbiting, its velocity is slower, but its orbital period is shorter. We'll get to that. Stuff in the middle gets pulled up towards the planet and ends up sticking to the planet in a process we call accretion. Versus on the outside, it gets slowed down a little bit, pulled in, actually sped up in real velocity terms. But that also ends up impacting the planet and sticking to it. And so it's just sucking in the mass from either side. For a better cartoon artist, I'd been able to show you that. Instead, I used arrows. Sorry. I don't have astronomy pictures of this because there are pictures, but not that are sharp enough to show this. So we know this from models, not from we've taken photos of it. Well, what does that material look like? What's the stuff in the solar nebula, in the planetary nebula that's forming there? Well, this is what we call chondrites. Chondrites are meteorites that we've seen, so there are pieces left over from building planets that do occasionally fall to the Earth, and we collect them. One of the things I love about studying meteorites is you get to say, I'm a geologist, I just want my rocks to fall out of the sky. And it's literally true. Chondrites are leftover pieces of planet forming that fell out of the sky, we found on the ground and we can study. There are a few neat features in them. You see all these little circles throughout? Those are what are called chondrules. They're normal rocks, what we call silicate rocks, but they formed as liquid droplets that were free-floating in space. So they formed little spheres. They cooled off, they quenched, they formed their different things, but they had to do this outside of a planet. Otherwise, it would have had an aerodynamic shape, or be a lens shape, or anything other than a sphere. There's also other stuff in there, like this here is what's called a calcium aluminum inclusion, or a CAI. These are vapor-deposited high-temperature minerals that form directly from the solar nebula without ever becoming a liquid. And he gives us some temperature constraints on this and says, where that stuff formed, it was hot, which makes sense for making droplets of molten rock that are floating around too. But most of these rocks are made up of dust, little bits that never melted, never made anything bigger, but eventually came together to stick this rock together. There's also little pieces of iron flecks, a bunch of other stuff that's in there. That's your basic idea of what's there. Okay, so this is the primitive stuff. That doesn't look anything like the Earth, though. So how do we go from this to something that looks like the Earth? This is a process we call differentiation. You start off with an undifferentiated planet. You have a chondrite. It's got these chondrules, it's got metal mixed in, it's just a bunch of stuff in a giant garbage can of whatever got swept up there. Well, what happens as it starts to pile up is it starts to heat up. And there's a few different ways that can happen. First one is if you think about an impact, that's what we call gravitational heating. Something came down and hit the ground. That leaves a lot of heat behind. But that's not actually the main way that these get heated up. It gets heated up because of radioactive decay. In the early solar system, there were 4.6 billion years worth of more radioisotopes than there are today. So there's a lot more radiation, and that's what caused everything in the solar system to heat up. When it built up into a big ball, it insulated itself so that heat could pile up instead of just radiating off into space. When that happened, the things started to gravitationally separate, or what I will call differentiate. Those little flecks of iron have a density that's close to 8 grams per cubic centimeter versus a normal rock is 3 grams per cubic centimeter. So they're very negatively buoyant, they sink. Think of it like an anchor being thrown off your ship. It's not going to float in water, density 1 gram per cubic centimeter, it's going to sink to the bottom. Iron did the same thing here, and didn't have to melt much for that to sink all the way in, and that forms a core. At the same time, any of the rock that's melting, well, molten rock is less dense than the solid rock that it came from, and so it tries to go up towards the surface, and you end up making big pools of lava all around the surface of these bodies. A very long and complicated story later, which I will happily get into if you want to take a full course on geochemistry, we end up with something that looks like this, where you have an iron core, with some other stuff like nickel and a couple other elements. Then you have a mantle, which is the interior of the planet. In our case, it's mostly olivine and high-pressure forms of olivine. And then a crust, which is also rock, just like the mantle, but a little chemically different, and how so needs that course in geochemistry that I don't want to do tonight. Sorry. Do we see things that look like this out in the solar system? Turns out we do. One of my favorite asteroids is named Vesta, and it's a differentiated asteroid. It's mostly spherical, and its surface has a basaltic crust, and its interior has a different composition inside. It's orthoperoxenite and dunite. Don't worry about what that means. It's different materials in the middle, and then we believe it has an iron core, but we've never actually seen a core sample of Vesta. How do we know about this? Well, we sent a spacecraft to visit it, which is where this picture came from. This is looking down on Vesta's northern pole from the Dawn spacecraft. But we also have meteorites. The Howardite, Eucrite, and Diagenite, or HED meteorites, either came from Vesta or something just like it. And so we can study them in the lab and learn a ton about how this system would have worked, how it evolved, what happened to go from that primitive stuff to the things we now see that exist in the solar system. If we look closer at Vesta, we can get morphology, topography, talk about what's really there. This is a topo map of Vesta where there's red is the highlands, blue is the lowlands, and you can see mostly it's craters that have scooped up and gone down. It's a very pockmarked and cratered surface. Honestly, to me it looks a lot like the moon, just much, much smaller. One of the really neat features on Vesta though, and one of the reasons why I bring it up, is it's got these two giant impact craters on the southern pole. These impact craters were so big relative to Vesta that the shock wave from the impact popped back out and made these linear features around the planetesimal. And those ridges are literally that shock wave blowing through. If they were much bigger, it would have blown it apart. It would have been like this thing took a shot and just shattered. That definitely happened. And that's what we see for most of the asteroids that we see. Whereas Vesta is what my wife likes to call a lumpy dinosaur egg. It's a protoplanet that never accreted into a full-size planet anywhere. Most asteroids are like the asteroid Bennu, where they're a rubble pile, a garbage can. It's just pieces of fragments of other stuff that happen to end up getting added back together afterwards. Okay, so if we want to know even more detail about the solar system, and I hope I haven't overwhelmed you yet, we have to start to ask questions about where are things in the solar system? So here's a plot of the position of the planets as of the 28th, so 3 days ago. There's a wonderful service that the Jet Propulsion Lab has, that's the Solar System Dynamics Observatory, and you can go there and you can inquire about any object in the solar system that you can name. It will look it up for you and say, here's its orbit, we'll plot it, here's a 3D picture of where things are. This is looking down on the solar system, and it's the inner solar system, literally where things were 3 days ago, which hasn't changed much. If you want to talk about where it is, a handy way to talk about it is how far away from the sun is it? We've got Mercury, that's 0.4 AU. Well, what's an AU? It's an astronomical unit. It's a handy unit of measure, which is how far away is the sun from the Earth on average, hence the Earth being 1 AU. We then have Venus at 0.7, Earth at 1, Mars at 1.5. Another way to look at this is, how long is the year? The closer you are into the object you're orbiting, the slower you're going. But the shorter your year is. That is, the less time it takes you to go the whole way around. That's because while you're slower, you're at a lower energy orbit when you're closer, the track you had was a lot shorter. Put another way, if you're going faster, you'll travel further out in the solar system. But it'll take you longer to go around the solar system because the track got so much longer in front of you. So the length of the year on each of these places, Earth's year is 365 days. Mercury's year is 88 days because it's got such a short track compared to what the Earth has. Mars is almost 2 years long. If we take a step a little bit further out in the solar system, here's Jupiter and Saturn included in the picture. You can still see Mars, Earth, Mercury, and Venus in the inner solar system and the Sun. And those distances are a lot longer, and the length of their years are a lot longer. One of the really neat things that you see is there's a kind of orderly progression in these different planets. I probably should have put this on the slide too, sorry. Mercury was 0.8 AU, Venus was about double that, Earth was not quite double that, Mars was about double Earth's distance out. Then Jupiter is a full doubling of that, again, up to 5.2 AU. That's a really big step between Mars and Jupiter. And then Saturn's just another step out further. Yeah.
So it takes Saturn 29 years to orbit the sun.
Yes.
That's a long time.
It's a very long time. If I were living on Saturn, I would be a 1-year-old. And you wouldn't be at your first birthday yet. Pretty cool, right?
Yeah.
It'd be very hard to keep track of age. So, what's missing between these is actually the asteroid belt. There should have been a planet there. Why isn't there a planet there? Well, it turns out Jupiter's a really big bully, gravitationally speaking. Anything that gets close to Jupiter, Jupiter wants to gobble up. Now, this is the average distance the asteroid belt is, about 2.7 AUs. If you plot the full range, it looks something more like this. It's kind of spread out over that interval. And there are parts of it that are missing. I hope this isn't too technical, but what's going on is anytime you have a lot of encounters with Jupiter, which means your orbital period is in a small ratio with Jupiter's, like 3-to-1 or 2-to-1, you encounter Jupiter too often and it eventually either gobbles you up or kicks you out. It bullies you out of your orbit. And so what's shown here is how many asteroids are in each small step along this axis versus how far from the sun is it. Where this is the full range of the asteroid belt, about 2 to about 3 astronomical units. And there are places where there's nothing in there. And those are where it's in a tight resonance with Jupiter. And so Jupiter's just gobbled it up, kicked it out, gotten rid of it. It's not there anymore. Kind of cool, right? Well, there are a few other asteroid populations that you might want to know about. There's some near-Earth objects. Those are typically things that Jupiter has badgered into the inner solar system. So they're in Earth-crossing orbits or near-Earth orbits. Asteroid Bennu is a great example of that. But if we want to talk about other populations, we need to talk about Lagrange points. Who here knows what a Lagrange point is? Who here wants to know what a Lagrange point is? Great, I'm glad. If there were no hands raised on the second one, I'd be in trouble. So, Lagrange points are places where there's a gravitational balance between the parent and the orbiting body. In this case, I've got the Sun and I've got Jupiter shown there. But this works for any two objects where one is orbiting the other. Lagrange points happen along a line, which I've drawn as horizontal, but it connects the middle of one body to the middle of the other. L1, the first Lagrange point, is literally where there's just as much gravity pulling you towards the thing you're orbiting as there is pulling you towards the thing that's doing the orbiting. So if this is Jupiter and this is the Sun, there's a spot in between Jupiter and the Sun, much closer to Jupiter, where Jupiter is pulling you as hard up as the Sun is pulling you down. That means you end up in the same orbit as Jupiter, but closer in towards the Sun, which wouldn't normally be possible. The closer in you go, the shorter your period is. So you go around faster and faster. Well, slower and slower, but over a shorter period of time. Sorry, orbital dynamics is fun. I swear. L2 makes slightly less sense. It's actually further out. And what's going on is that now you've got the Sun and Jupiter both pulling you down, which makes it act like there's a bigger Sun or Sun that's closer to you. And so even though you're further out and it should be a longer period to go around, you're going actually faster. So you're covering that track in just as much time as the inner track. And so you're staying in that position above Jupiter. That's L2, which will not be relevant for any more of this discussion, so feel free to ignore it. L3 is a really weird point. It is a pinpoint on the far side. It's in Jupiter's orbit. It's the one spot furthest from Jupiter where Jupiter's not really doing anything to you. But it's literally a pinpoint. You go a foot to one side or the other side, and given astronomical time, Jupiter will pull you towards itself and you won't be there anymore. It is the least stable place to be relative to a planet. But it is stable if you can get there. Now, for L4 and L5, they get a little more complicated. But it turns out they're the most relevant Lagrange points because they're the ones that are the most stable. About 30 degrees forward or backwards in the planet's orbit are these 2 points. The lead one we call 4, the follow one we call 5. Doesn't matter too much which one's which. If you draw an equilateral triangle, you'll be in about the right spot. And what's cool about these spots is they're not just spots. They're these smeared out zones where if you get a little ways ahead of Jupiter in that, Jupiter will pull you back towards the spot. And you'll end up oscillating back towards Jupiter. But you get too far back from that spot, and the sun will pull you forward because it wanted you to go faster than you were just doing. And so you end up in this gravitational bottle where you just kind of oscillate back and forth over this zone. And you don't really end up leaving there unless something else comes along to kick you out. And so it's the most stable place for asteroids to be floating around in. Now, show me that it happens or it didn't happen. This is great theory. What we've got on Jupiter are two large populations of asteroids that share its orbit. We would call all of these sorts of asteroids Trojans. But because we want to make things even more complicated, there's the Trojans and the Greeks, the lead and the follow in Jupiter's orbits. If you know your mythology, that's funny. If you don't, go blame an astronomer. It turns out there are Trojan asteroids around every single planet. Earth, Mars, Saturn should have a large population, but it's too close to the bully of Jupiter, so it's only just a couple years ago where we found the first one. Went, yes, finally, we can say all of them! Well, Jupiter's a bully, so the largest population, aside from Jupiter, is actually Neptune. Go figure. I'm going to go ahead and skip the next part because I love this asteroid population, but it gets really messy to describe. Something called the Hildas. They end up somewhere along this triangle in terms of position, all in orbits that are just barely missing Jupiter every single time they orbit. They're weird and wonderful. I highly recommend looking up their Wikipedia entry because there's some fantastic animations that just go, you can't orbit as a triangle, except they do. If we step a little bit further out, finally see Uranus and Neptune, and I'm sure many of you have been wanting to see Pluto. There's Pluto. What's the thing you notice that's different about Pluto than every other planet that we've seen so far?
Pluto intersects with Neptune.
Yeah, Pluto's orbit crosses closer in than Neptune's does. If you want to be a little more detailed about it, its orbit is less circular, and because it's less circular, the sun is not directly in the middle, it's on one of the two foci of the ellipse. So everything looks a little skewed. It'd look even worse if I'd had the time to show you the view looking horizontally into this, along what we call the ecliptic, because all the planets are sitting in the same plane, except Pluto that's off at like 45 degrees. So Pluto really doesn't belong. Yeah.
Will Pluto and Neptune eventually crash?
No, actually. And the reason why is because their orbits are what's called skew. So you can have orbits that are parallel, which is what's going on with all of these other orbits. They're always on parallel tracks, they never intersect. You can have them that are actually crossing, where they do cross each other, and at some point, they will eventually hit each other. Or, what doesn't show well in this kind of plot is they can just be looking like they're overlapping, but never actually truly crossing. Pluto's orbit does come closer to the sun than Neptune, but never actually crosses Neptune's orbit. So they're never going to actually cross. Very good question. Sorry for the geometry. Yeah.
Is Pluto a real planet?
That depends on what you mean. There's a big group of scientists that I'm not part of called the International Astronomical Union that decided Pluto is not a planet. And the reason why is because Pluto doesn't look like the other 8 planets. It does something that's different. It's sort of like Ceres actually looks a lot like the other planets, but there's something that's just not quite the same about it. Does that make sense?
Yeah.
So because we want to describe things that are similar to help us understand how they came about, when we saw that Pluto was so different, we said it probably belongs in a different group by itself. That started the conversation. What ended it was when we found a whole bunch of other objects just like Pluto. Sedna, Haumea. These are other things that share these kind of wacky orbits. They're even further out though, so it took us even longer to discover them, both because there was less ambient light to see them, and in many cases they're smaller. But there's a whole family of things that just don't quite belong like the other planets. Turns out these are what we call Kuiper Belt objects. All right, so who wants to actually talk about planets now? Excellent. Let's start off with Mercury. Mercury is the closest planet into the sun. What does that kind of look like to you?
The moon.
The moon, yeah. It's kind of a dull gray. I think this is actually being color stretched a little bit, but you can see a few places that have slightly different colors. It's pockmarked. You can see scars from where there's impact ejecta coming away from some of these impacts. We call rays. If you look at the topo map of the surface, which is what this is, yeah, it looks a lot like the moon. It's rugged. There are lowlands that are in blue. There are highlands that are in yellow. Green's kind of in between the two. And it's just kind of this rugged body surface. Mercury looks a lot like the moon because it's never had an atmosphere. It's never had a ton of volcanic process. There are volcanoes in there, but didn't make giant flood basalts, which, by the way, is one of the things that looks rather different about the moon. The biggest difference with the moon from Mercury, from just looking at it, is you've got light patches and you've got dark patches. And the dark patches tend to be smoother than the light patches, which you can really see on a topo map. I really ought to make a topo map that has a higher color distinction than this one does. But those dark patches on the moon are these portions here. They're what's called the mare, which, if I remember right, is Italian for sea. I know it means sea. I forget if it's Italian or Latin. But when they looked at this, they said these are very, very flat. That's probably what the ocean would look like if we're viewing it from somewhere not on the Earth. Versus the highlands material is this rough and jagged terrain. The near side of the moon is about here. That's the far side of the moon. The far side's even rougher than the near side, which is kind of a weird detail about the moon. Well, the moon's one of the planets we've seen up close. So here's what the surface of the moon looks like. You can see there's lots of rocks, there's lots of dust. It's all gray, it's all kind of smoothed over except where there's rocks. What's going on there is there's something called regolith. Regolith is what happens when one rock hits another and it pulverizes it and then spreads it all around. The moon has had billions of years of rocks hitting it and then nothing else happens. So it hits, it smashes it, and the debris goes flying everywhere and it makes this thick layer of rock powder. That's the regolith. There are other features on the moon, though. One of my favorite places is called the Marius Hills, and this is the edge of Marius Hills. We've got two sinuous rills. Here's a volcanic vent that formed a lava lake that then made this long stream that appears to have eroded its way into the landscape until it comes out into the mare, a sea of just volcanic plains, where it's just eruption after eruption after eruption, literally like an ocean, but made out of basalt. Here's another one that seems to have some sort of tectonic control on the vent, a lot like Mauna Loa. But then it forms this long sinuous rill that does the same thing and empties into it. There's another place nearby called Aristarchus, where you can see, here's a really big impact crater. In fact, you can see, even the topo map, the rays radiating away from that impact crater. It's got little central cones, impact. Versus over here is a really big lava lake that was the top of a volcanic vent. And here's another one of those sinuous rills that actually even has a smaller sinuous rill inside of it that was doing the same kind of thing and slowly filling up those flood plains. So it's a volcanic history that's imitating some of the things we see on Earth, but it's not doing the same stuff. Now we've got my favorite planet, Mars. Mars looks really different from everything we've seen. What's one of the first things you notice about it?
Red.
It's red. Why is it red?
Iron.
Iron. Specifically, it's iron oxide. Literally, it's rocks that have rusted. What happens is water gets into the rock and it pulls out some of the iron and it forms rust. It literally has rusted. That's why it's so bright red. But there are a few other odd things about Mars. Here's a topo map of the surface. Remember in the other ones where the low-lying areas were kind of interspersed somewhat randomly with the high-lying areas? In Mars, they're pretty well sorted. The northern hemisphere is low, the southern hemisphere is high, with a few exceptions. But this is a weird planet-wide feature where we've got this dichotomy between them. We've also got the texture of the northern plains is very smooth compared to this rough, jagged, pockmarked, cratered all to everything southern terrain. You've also got these giant volcanoes. They're not making flood basalts like you were seeing on the moon, or for that matter on Mercury. They're making these giant volcanic edifices. This one here is one of my personal favorites. It's Olympus Mons, largest volcano in the entire solar system. It's 27 kilometers tall. For comparison, Everest is about 5. Olympus Mons is so big that if you viewed it from low Mars orbit, it would actually bulge out the side of the limb of the planet. The top of the volcano is in space. It is huge. This is a computer rendering because our satellite would die fast if it were this close, but that's about what it would look like. And the surface has evidence of streams and aeolian process, meaning wind-blown dunes. So you've got rocks that were formed in lake beds, and you've got piles of dunes like the shifting Sahara Desert, where winds blow that sand back and forth. This is very different from the other worlds we've seen. Yeah.
That looks like the beach.
It actually does. And you're not far wrong. This is in Gale Crater, and it's looking towards Mount Sharp, which is in the distance here. This is some of our first encounters with, oh goodness, I'm going to mess up the names of the dune fields, so I'm not going to try. These are some of the dune fields that surround the crater. We actually think that that Gale Crater, it formed from an impact, but when Mars was wet, and so it became a lake, and then that filled up with lake sediments, and then Mars dried out. And then winds blew in and slowly eroded out the bottom of that lake and left dunes like that behind. So that there's actually modern dunes that are sand slowly scouring the surface, going back and forth over it. And that's what those are. Great question. Or great observation, I should say. Next place we'll look at is Venus. Venus is really cloudy. And it's because it has atmosphere and way too much of it. It's so much atmosphere that it is incredibly hot. I actually forgot to look up the number of Venus's surface, but it's something like 1,000 Celsius on the surface. And the pressure is so high that if you think about how viscous the atmosphere is, how hard it is for it to flow, it's closer to honey on the surface than it is to air. If you want to land on Venus, you don't need retro rockets. You don't need a parachute. In fact, you don't want either. You want to sink fast enough in that atmosphere that it doesn't crush you before you get to the bottom. The Soviet Union's the only ones who have ever landed on the surface, and I'll show you a picture of that in a minute. And the way they did it is they made a shot put, a sphere that could withstand that pressure for as long as possible, and literally let it just sink through the air to get to the ground. Lasted a few hours. We can't see the surface with the naked eye, so this is actually a radar image of what the surface looks like, colorized to what we know of the surface from the few landers that have made it. If you want to see this in terms of a topo map, it looks something like this. And we start to see some things that are getting a little bit different here. We've got lowlands again and highlands. I apologize, the colors aren't the same between all of these. Blame the USGS, not me, but don't actually, because, yeah, it's hard to be a civil servant right now. But we've got things that start to look like continents floating in an ocean, rather than what we've been seeing elsewhere, which is where the low-lying stuff is a little bit weird, or maybe on the northern hemisphere. This is actually looking more like Earth than anywhere else we've seen, although it's not the whole way there yet, and it's definitely weird and alien. I mean, one of my favorite features, I forgot to pull an image of, the atmosphere is so thick that when meteorite comes in to impact the ground, the meteorites shatter, and so you get a shotgun effect hitting the ground. You get these honeycomb impact craters, because you had dozens of things impacting, not one, because even the strongest impactor didn't make it. Anyway, Venus is weird and wonderful. This is what the surface looks like. This is a colorized image, but it's based off of a real color wheel, so this is as close as we can match to what it would actually look like if you were there. You wouldn't see it for long if you were there, because you'd be squished, burnt, and then destroyed by sulfuric acid. Enjoy! Now we've got a truly weird planet coming up, Earth. Earth is odd. If you look at a topo map of Earth, again, I apologize, it's on a different color scale. Lowlands are blue, which is common. The highlands are brown and intermediate is green. Yeah, they're being cutesy. They also colorize things that are usually ice covered with white. I'm sorry. Again, blame but don't blame the civil servants. You can see that there are highland materials that are distributed in different ways. In fact, there's odd things like the shape of the edge of Africa lines up with the shape of the edge of South America. There's something weird going on with the Earth. Turns out the answer is plate tectonics, and I'll let somebody else teach you about that. But there's a whole bunch of volcanoes, there's a whole bunch of other features, and the surface is just odd compared to everywhere else. And that's before you talk about there being water, which, yes, there was some water on Mars at one time, but there isn't presently. Water's usually in the outer solar system. We'll get there. I'm going to skip right past Ceres because I am talking way too much. Into the outer solar system. Here's Jupiter. Jupiter has 101 confirmed moons as of this past March. That's a lot. I'm going to talk about 4 of them. These are the 4 Galilean satellites, the largest ones that are closest into Jupiter. And these probably formed relative to the Jupiter, same way that planets formed relative to the sun. That is, there was a planetary nebula around Jupiter that formed moons. Well, most of the material fell into Jupiter, but some of it stayed in orbit. 4 things did that for Jupiter. Most of the rest of those moons are captured asteroids or Kuiper Belt objects or other things that formed elsewhere in the solar system, and Jupiter said, yoink, mine. Io is one of my favorite places. It's the closest in moon to Jupiter, and it's one of the few places in the solar system we absolutely positively know is volcanically active right now. Do you know how we know that? We literally captured a picture of a volcano erupting into orbit on Io. I believe we've done that more than once. I think this is the reprocessed Voyager image. I honestly forget because I've had this picture for a while. But we literally captured a sulfur plume coming off of one of the volcanoes on the surface of Io. Now, the volcanism on Io is a little weird and different compared to everywhere else. On Earth, there are kind of 3 things that drive volcanoes: water and subduction zones, heat coming off the core, and crust pulling apart, making mid-ocean ridges. Again, different lecture. Io, what's going on that's driving all of this is the fact that it's in tug-of-war between Jupiter and the other Galilean satellites. Europa, Ganymede, and Callisto are trying to pull Io further out away from Jupiter, and Jupiter's trying to pull it back. The net result is Io's getting melted on the inside and belching its guts out into orbit. It's actually totally weird and totally cool. It turns out to be a really important process in the outer solar system. But all these colors that you see are different species of sulfur. You really liked knowing why things are colored? Io's answer is sulfur. There's yellow sulfur, white sulfur, red sulfur, black sulfur. They're all just different bonds within sulfur molecules, which turn out to be brightly colored. Next moon out is Europa. Europa is crisscrossed by all of these lines. These are transform faults, we think. What's going on is Europa has an icy shell. Ice is one of the weirdest minerals in the world because it's less dense than the liquid it came from. It floats on top of your glass of water. And so Europa has an icy crust, but it's also in this tug-of-war between the other moons and Jupiter. And so its inside is hot enough, there's a liquid water ocean underneath that. There's almost certainly a rocky core, maybe even a high-pressure ice shell outside of that, but there's an ocean under that which lets the surface run across each other. Now, because ice is also less dense than water that it came from, it doesn't have plate tectonics like the Earth does. The crust actually wants to sink back down into the Earth because it's more dense than the liquids it came from. Yes, I said that right. Doesn't work for water. This stuff is all buoyant on top of it, so it can slide past. You can't subduct. You can't make the normal sorts of tectonics we think of on the Earth. Ganymede is some of the same stuff, but a much coarser scale, which means it's a lot less active. This means that if there's an ocean, and we think there is, underneath the surface of Ganymede, it's a lot thinner, and it may not be worldwide. It may just be localized or interconnected in small portions. It may be more like water lakes instead of water oceans. And Callisto, on the other hand, kind of looks like a pockmarked moon. Oh, sorry, I missed it.
The moon 2 moons before this.
Europa.
Yeah, is there life in the ocean?
That's an excellent question. I don't know. As a matter of fact, nobody knows. We would love to find out, though. There's actually a mission going to Europa to try to answer some of the questions we need to get to that question, called Europa Clipper. It's going to land on the surface and it's going to orbit Europa and get more detailed information so we have better leverage of how would we actually answer that question. Because it's really hard to explore somewhere like Europa. If you want to look into the ocean, You may have to drill through 100 kilometers of ice to get to that ocean. I forget the real number, but it's not a few kilometers, it's a lot. And it turns out radio signals don't go through large chunks of ice very well, so you need a cable that went along behind you, but it's not going to be a water-filled hole, it's going to freeze itself back up behind you, so how do you do that? That's really hard to do remotely. With people there, maybe, but with robots, it's really hard. So we need to ask questions that we can answer to get us towards how might we answer the ones we really want to know, like, is there life? It's a great question. Yeah.
I have a way you could find out. While you're drilling, you could have something hot with you and just put it at the top so it wouldn't freeze up.
So we've actually thought about doing this. When I mentioned drilling, I'm being euphemistic about that. The main way people think about drilling is putting a drill bit that is in fact a piece of hot plutonium on the front of the drill, so it just melts its way down. It's a lot simpler than it is to have a rotary drill digging in, but it's also complicated for other reasons, like you have a large block of plutonium. So it's a great idea, but it turns out that's a long ways to keep hot all at once. And even if you did manage it, I'm not sure we want to poke a hole all the way through the crust, because we might inadvertently make a volcano where the ocean pops out the top. It's like if you took a Capri Sun and put it under some pressure and start stabbing at it with a straw. I'm not sure you want to succeed at that, because I think you're about to need to change your clothes. Callisto looks very different from Europa and Ganymede, and it's because it's the furthest out of these big moons, so it doesn't have that same kind of tidal heating. It might have some, but we don't really think it has the same kind of ocean, and it doesn't show the same surface features. In fact, you can compare them pretty well. Here's Europa's surface, Ganymede's, and Callisto's, with the same sort of features between each, but you can see it's going from, this looks like it moved a lot. There's a lot of fine detail, a lot of things that shifted on it. Ganymede, it's a lot coarser. It doesn't seem like it's happening as regularly. Callisto, if it's happening at all, it's not obvious. But these surfaces are all made out of the same stuff. It's mostly ice. So that kind of tells you some about what's going on inside. All right, I promised I'd talk about Saturn. Here's Saturn. Beautiful rings, beautiful world. Saturn's rings are one of its most iconic characteristics. You can see all these fine little details coming through them. This is from the Cassini mission, which actually, towards the end of the mission, flew inside of the rings, which is an incredible technical feat that I'm not sure I would have attempted, because there's not nothing in between the rings, and so there's a chance you'll hit something. And you don't so much find out what you hit as you found out that you didn't hear anything anymore ever again. Anyway, it's really cool. If you look at the rings in some detail, past the big obvious ones that you'll see with telescopes, they're very diffuse, faint ones, including this furthest one out here, which, if I remember right, is called the F ring. And what's neat about that one, it's very diffuse, unlike the inner ones. It's wider, so it's not in this really narrow plane, unlike the inner rings. What we think is happening is that the moon Enceladus is populating that ring. Enceladus is an icy satellite that's just a little ways outside of the F ring. And what's going on is it has geysers. Some people refer to these as the tiger stripes because it kind of looks like a claw mark on the southern pole. Those cracks, this is colorized, I'm sorry, that's not true color. Those cracks, we think, are massive geysers that actually don't just erupt onto the surface, but erupt so hard it goes out of Enceladus' orbit into Saturn's orbit and is slowly filling up that ring with little ice crystals that eventually someday will form a nice uniform ring. Someday. The other really cool moon of Saturn is Titan. It's a big fuzzy cloud. The reason why it's a big fuzzy cloud is because it's got hydrocarbons all through its atmosphere, and its surface is ice. You can't see the ground under normal light. If you look through, you start to see this kind of stuff, where you've got what looks like it might be highlands and what looks like it might be lowlands, but that's just an albedo difference. That's not actually topography that I'm showing there, it's just what color it shows up as. If you do interpret the topography, you start to find out that there are lakes on the surface of Titan. and there are highlands and mountains. Here's where it gets really weird. The highlands and mountains are made out of ice that's so cold it's behaving more like rock than what we usually think of as ice. And the lakes are made out of hydrocarbons, things like methane. And so you've got organic atmosphere that's cycling and raining and making streams and making lakes. And that's really weird from a chemist's point of view. The surface looks a lot like a normal river surface. We have one lander that went there, the Huygens probe that was deployed by Cassini. And it looks like river cobbles. Those are ice boulders that are sitting there in a stream bed that was plowed by hydrocarbons. What makes the sand? I'm not sure, but it's not rocks. Uranus is a particularly weird planet, not just because of the name. If you look at it in different light, you can see it's actually tilted on its side. It orbits with one end facing towards the sun, as opposed to all the others where it faces up and down in the ecliptic plane, so it does this. Uranus does this as it goes, the finger pointing in towards the sun. Also has a tiny ring. I'm not going to say anything else about it because it's a gas giant, so I don't care. Here's Neptune. Similar story. Gas giant, don't care. It's pretty neat, but I'm out of time, so... It has a moon called Triton that's so cold it actually has nitrogen that cycles. It's a nitrogen atmosphere. It has what appears to be nitrogen rain and nitrogen ice on the surface. So there's the full cycle, just like we see with water ice, with nitrogen on Triton. For those of you that know about liquid nitrogen, it's a good way to make ice cream or to freeze literally anything you want to on the Earth. So it's very cold. Because I'm sure somebody wants to know about Pluto. This is Pluto, as was seen during the one flyby pass we got from New Horizons. Pluto's fascinating for a lot of reasons. One of the ones that I really like to talk about is the bladed terrains. This is what it looks like if you zoom in on some portions of Pluto. Does that remind anyone of freezer burn? That's basically what that is. We think those are what are called penitentes. These are ice formations that happen at high altitudes near the equator. Just a minute. Where the sun is ablating it and it makes these features that are kind of look like kneeling monks in rows that are about the size of a person. These ones are the size of Manhattan skyscrapers, and even though the sun only just looks like a midly bright star in the sky, not like the sun as we think of it, they still point at the sun. So these things are really old. The other really fun one is what we call Sputnik Planitia. It's the heart of Pluto. This thing right here. These are little convective cells of nitrogen ice. The thin atmosphere on Pluto is nitrogen, and when it gets further out from the sun, that freezes and forms these ice blocks. There's evidence that these things are convecting and make these little convective cells that says that geology is still active, even though this thing is about 45 astronomical units away from the sun. That's crazy. No one predicted that. Yeah.
Are there moons on Pluto?
Pluto does have a moon. Pluto actually is part of a 5-object system. I think there may be a couple others, but the two main ones are Pluto and Charon, which is named again from Greek mythology. Charon is so large relative to Pluto that the two actually orbit each other more than they orbit around the center of one of them. So this is where we start introducing terms like barycenter. So every two objects that orbit around a common gravitational center. On the Earth, that's indistinguishable from the middle of the Earth. On the Sun, that's indistinguishable from the middle of the Sun. Pluto and Charon, it's external to Pluto. And so you see Pluto doing these little loops around the barycenter and Charon doing these bigger loops around the barycenter. So the two kind of do this fun dance back and forth around that center that's external to both. It looks really weird. There are a couple more moons, 3 of them if I recall, that are further out than that. We know even less about them because they weren't well photographed. And it's really far out in the solar system. Good question. One last thing before we wrap up, and I've gone way over and I apologize. When you get into comets, we flew past an object named Arrokoth. It was originally referred to as Ultima Thule until someone realized that was a white nationalist reference that we didn't want to make. But the two lobes are still called Ultima and Thule, so whatever. these are two things that just kind of floated towards each other and stuck. You can see there's a sphere here and a sphere here, and a place where they just stuck together and kind of formed a little bit of a neck. It's not very mature. It really just looks like these two spheres stuck to each other. Well, if you look at comets, and you look into the nucleus of the centers, you start to see similar sorts of things. A rock, another rock, stuck together with this kind of weird neck feature. And it's not alone. Here's another comet. Big piece, low ground in between them, where it looks like two objects stuck together. So this seems to be the kind of thing that happens to stuff way in the outer solar system. It just slowly bumps into each other. Sure, there's still impact craters. There's stuff that come in at high velocity, but they don't have these big catastrophic bangs like we had in the inner solar system. They just sort of go thunk. Okay, we're good. Anyway, there's your brief tour of the solar system.